Hello students, welcome back to class 12 mathematics. Let me ask you something interesting. Have you ever tried to draw the sharp tip of a triangle with a ruler and then thought, wait, what would be the slope of a tangent exactly at that corner? That very puzzle leads us to the idea of differentiability. Continuity alone isn't enough because even though the function may look unbroken, if the slope of the tangent is not well defined, differentiability fails. Today, we will carefully explore what makes a function differentiable. Differentiability is all about the existence of the derivative at a point. A function f is differentiable at x equals if its derivative exists as a finite value. Formally, we write f dash of a equals limit as h approaches 0 of f of a plus h minus f of a whole divided by h equation 1. Geometrically, this represents the slope of the tangent at the point x equals a. If that slope is smooth and unique, the function is differentiable. But if there's a corner, cusp, or vertical tangent, then the derivative does not exist. Now let's formalize the idea. A function f of x is said to be differentiable at x equals if the following limit exists: f dash of a equals limit as h tends to 0 of bracket f of a plus h minus f of a bracket divided by h. This is called the difference quotient. If the limit exists and is finite, then the derivative at that point is well defined. In simple words, differentiability is nothing but the ability of the function to have a unique slope at the point. For example, take f of x equals x squared. At x equals 2, we can apply this definition and confirm that the derivative exists. But wait, for the limit to exist, it must give the same value from both directions. That's where left-hand derivative and right-hand derivative come in. The right-hand derivative is defined as limit as h tends to 0 from the positive side of bracket f of a plus h minus f of a divided by h. The left-hand derivative is defined as limit as h tends to 0 from the negative side of bracket f of a plus h minus f of a bracket divided by h. For differentiability at x equals a, both left-hand derivative and right-hand derivative must exist and be equal. For example, in the case of f of x equals modulus of x at 0, the right-hand derivative is plus 1 while the left-hand derivative is minus 1. Since they are not equal, the function is not differentiable at 0. Now let's compare continuity and differentiability. Differentiability always implies continuity, but continuity alone does not guarantee differentiability. Take again the function f of x equals modulus of x. It is continuous at 0, but as we saw earlier, it is not differentiable there because of the corner. Other examples include cusps and vertical tangents. For instance, f of x equals x raised to the power 2/3 has a cusp at 0, and f of x equals cube root of x has a vertical tangent at 0. These graphs are continuous but fail to be differentiable at those points. So, differentiability is a stricter property than continuity, ensuring smoothness beyond just connectedness. So far, we talked about differentiability at a point. What about intervals? A function is said to be differentiable in an open interval bracket a comma b bracket if it is differentiable at every point inside that interval. For a closed interval square bracket a comma b square bracket, the rule is slightly different. At the left end point a, we only check the right-hand derivative, and at the right end point b, we only check the left-hand derivative. For example, polynomial functions like f of x equals x cubed or f of x equals x squared are differentiable everywhere on the real line, including all intervals. This makes them some of the smoothest functions we know. Let's test this with an example. Suppose we want to check differentiability of f of x equals x squared for all real numbers. is equal to, we start with the definition, f dash of a equals limit as h tends to 0 of bracket f of a plus h minus f of a bracket divided by h substitute equals limit as h tends to 0 of bracket open a plus h close squared minus a squared divided by h. Simplify the numerator, a squared plus 2 h plus h squared minus a squared, which gives 2 h plus h squared. Now divide by h to get to a plus h. As h tends to 0, this becomes 2a. So, the derivative exists for every real number a, which means f of x equals x squared is differentiable everywhere on the real line. Let's wrap up a discussion on differentiability. We began by defining it as the existence of a well-defined tangent or slope at a point. We saw the mathematical definition using the difference quotient, and we introduced left-hand and right-hand derivatives to ensure uniqueness of slope. We clarified that differentiability implies continuity, but continuity alone is not sufficient for differentiability, with examples like modulus x, cusps, and vertical tangents. We also extended differentiability to intervals, both open and closed. Finally, through the example of f of x equals x squared, we confirmed differentiability everywhere. And that's the complete foundation of differentiability, a stepping stone that allows us to dive deeper into differentiation techniques and advanced calculus. In the next lesson, we'll explore rules and applications of differentiation.